At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like this video, you'll love my self-help books. Learn more about them at rescueedu.com. Let's talk about Fischer projections and 3D bond-line structures. First, we'll talk briefly about Fischer projections. Fischer projections are a very old and stylized way to represent the stereochemistry of organic molecules. These days they are used only in carbohydrate, that is sugar chemistry, and sometimes in biochemistry. Otherwise, they are never used in routine organic chemistry. But sadly, they are still used by some professors when teaching stereochemistry to undergraduates, so we need to discuss them. In Fischer projections, the long carbon chain is vertical. For instance, we can flip the meso isomer of 2,3-dibromobutane on its side. In the real molecule, we have the horizontal groups at each chirality center pointing forward. The N carbons must then be pointing back. To get the Fischer projection, we flatten this molecule and have a cross at each chirality center. In a Fischer projection, the artificial convention is that all horizontal groups are understood to actually point forward, and all N groups are understood to actually point back. They are a rapid way to draw linear molecules with lots of chirality centers, but you have to memorize the conventions to make it work. We can also draw the two chiral stereoisomers of 2,3-dibromobutane using Fischer projections. Recall they are enantiomers of each other. Assigning RS configurations to Fischer projections is difficult, and we won't cover it. Fischer projections are only commonly used in carbohydrate chemistry. You need to draw the carbon chain with the carbonyl carbon at the top. Notice that all of these representations have a CH2OH at the bottom. In between, you have crosses for each chirality center. Here is a Fischer projection of one enantiomer of glyceraldehyde, the simplest carbohydrate. It has one chirality center with the OH pointing to the right. Erythros is a carbohydrate with one more chirality center. It too has the carbonyl at the top and a CH2OH at the bottom. Finally, this is the most important carbohydrate, glucose, also called blood sugar. It has four chirality centers which occur in this pattern. OHs are right, left, right, right. These first three compounds are the natural enantiomers of each sugar. They are called D sugars. We can tell they are D sugars because they have the hydroxyl on the last, that is the bottom chirality center, pointing to the right. The other enantiomer of glucose is L-glucose. It's called L because the hydroxyl at the last chirality center points to the left. L-glucose is the unnatural enantiomer and does not occur at all in higher organisms. In fact, all of the L series of carbohydrates are unnatural and very, very rare. Now, we'll learn about 3D bond-line structures. 3D bond-line structures are common, but it can be hard to evaluate the relationships between chiral molecules. If you have only one chirality center, it's easy to see what's going on. A and B and C and D are obviously enantiomers since the chirality center is inverted. You can also see that A is identical to C. You can simply rotate C 180 degrees in the plane of the paper to get A. Likewise, B and D are identical. You could also figure out these relationships by assigning configurations. You would see that A and C are both R, and B and D are both S. The relationship when you have two or more chirality centers in a bond line drawing is not obvious. For instance, E and F are actually enantiomers. These representations look like meso compounds at first glance because both bromines are pointing forward, but they are not meso. The true relationship is made clear if we convert the bond line drawings into Lewis structures and then compare. This allows us to line up the substituents, which makes evaluation easier. If we draw the Lewis structure of E and rotate the right-hand carbon, we get this representation, which is still E. If we draw the Lewis structure of F and rotate the left-hand carbon, we get this representation, which is still F. E and F are mirror images, but they are also non-superimposable, so they must be enantiomers. G and H are in fact identical, and so they are both G. G is a meso compound, which is not obvious from the bond line structure. If we draw the Lewis structure of G and rotate the right-hand carbon, we get this molecule, which is still G. You can see that all the substituents line up, and there is an internal plane of symmetry. So G must be meso. If we take H and rotate the left-hand carbon, we get this representation, which is still H. You can see it's the same as G. You should be careful in trying to evaluate 3D bond line structures for stereochemical relationships. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. My self-help books are particularly valuable in difficult learning situations, but you can also use them to get an edge or to get a head start. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.